Here we go for the special session of 200th ACS Science Talk. We have the speaker for today, Professor Hyun Jae Kim. Professor Kim is a leading expert in electronic materials and display technology. He earned his bachelor's degree from Yonsei University and completed both his master's and PhD at Columbia University, New York, USA. With nearly 3 decades of experience spanning both industry and academia, Professor Kim began his professional career as a principal engineer at Samsung Electronics. Since 2005, he has been serving as a professor in the School of Electrical and Electronic Engineering at Yonsei University and has been the director of the Samsung Display Yonsei University Display Research Center since 2014. Professor Kim is also deeply involved in leadership role within the global display and material research community. He currently serves as the deputy editor of the ACS Applied Electronic Materials, secretary of the Society for the Information Display, and a member of the National Academy of Engineering of Korea. In 2024, he also served as the president of the Korean Information Display Society. So thank you so much, Professor Kim, for joining us here for this special ACS Science Talk 200th session. The stage is all yours now. You can share your screen, Professor Kim.
Thank you so much. It'll be an honor. 200 Science Talk. And the celebration of ACS 150 years. Okay. Today, I'll be talking about new material, relatively new material as for many electronic devices, display, memory, sensor, and neuromorphic. Right? Okay. These are the content I'll be talking. I'll be briefly mention what is the oxide semiconductor and some fundamental thing, and here comes the applications. So display, memory, sensor, and neuromorphic, and one slide for the perspective of the oxide semiconductor. Right? Yes. What is this oxide semiconductor is for? This is quite, familiar. You're already familiar with all these electronic devices, iPhone, Galaxy and TV. And nowadays, this is very hot, right? Memory DRAM, semiconductor DRAM. This is for HBM. Yeah, DRAM they are considering using for this oxide semiconductor. This is sort of the future DRAM, 2T0C or 3D. I'll be briefly talking about this later in detail. And lastly, application is for the display and sensor, interactive display and neuromorphic. Neuromorphic is quite hot topic nowadays. Try to mimic the brain. So ultimate computing system is a neuromorphic system. So all these applications, people try to use this oxide semiconductor. The first one is already commercialized. For TV, more than 10 years, they've been using this oxide semiconductor. And iPhone and all this Galaxy, a few years back, they've been manufacturing using this oxide semiconductor. All right, so you probably heard the oxide material, especially inorganic. It could be insulator right here. One typical example is, oops, yeah. Yeah, example would be this is, insulators is very wide. Gate in the same, one example is the SiO2, very famous material for transistor. The second application is metal, but it's transparent. So some people call TCO, transparent conducting oxide, steel oxide. And lastly, semiconductor, insulator, metal, semiconductor. all for, inorganic oxide material. But this one, oxide semiconductor, specifically indium gallium zinc oxide, was, I mean, introduced by one Japanese professor 2004. And then after that, worldwide, many researchers only took 8 years become commercialized in iPad, I guess, by Sharp. Okay, so this inorganic oxide material for all purpose, insulator, metal, and even semiconductor. All right, so this is some research paper trend uh, based on, 25% of JCR, published journal SCI papers. Certainly, you can see the growing. This one is neuromorphic, photosensor, memory, and display. Okay, we know the oxide semiconductor research is expanding. Okay, is many people are researching on oxide semiconductor. So what's the fundamentals? Okay, when I say oxide semi, especially this one is for the commercialized one. This material is in your iPhone, and this material is in every home's OLED TV. Consists of indium, gallium, zinc, all metal. They have a different role though. Indium is for carriers, so mobility is for conducting. Gallium is the other way. It's reduce the carrier. And zinc is sort of the stabilizing the whole system. So this is silicon. For semiconductor, everybody knows silicon. Silicon is the wafer. Wafer is this crystal silicon. Okay, this is the wafer. And the conducting system in silicon, so when it comes down to transistor, just the silicon is the most representative material. But this is challenging. And they can be amorphous or crystal too. But used to be amorphous. Okay. Now this is hot topic. People try to crystallize this material to have a better performance of the device. Okay, but I'm telling you they have a different conducting mechanism. Okay. All right. This is the polysilicon. This is the grain boundary. There's a hurdle. You have to cross the hurdle. Electron must cross the hurdle. Okay, grain boundary is like amorphous. And this oxide semiconductor is not. It's different. This one is Fermi energy level. You know, you're changing the Fermi energy level, so this percolation called percolation conduction is expressing like this. Okay, so is different conduction mechanism compared to conventional silicon semiconductor. Okay, one more time, silicon semiconductor, you have to put some material. This is phosphorus. You put the phosphorus, they have one more extra electron, so it generates the electron, and this become N-type semiconductor. But for the oxide semiconductor, is you don't ion implant, this defect, oxygen vacancy. When you have oxygen vacancy, automatically you have two electrons. So oxygen vacancy means two electrons. Okay, so different mechanism. Okay, but this is a trade-off. You need to have oxygen vacancy in order to have electron. One more time, this is the defect, right? This is multi-component system. If you don't have the oxygen, you could consider as a defect, right? So it has both. You have to have oxygen vacancy, but not too many. If too many, it's defect and it's cause of instability, right? This is a trade-off. But the key word for oxide semiconductor is yes, oxygen vacancy. How do they make the oxide semiconductor? Conventional vacuum process, sputtering. Okay, sputtering, and then they control the knob, this gas flow, especially oxygen, partial pressure is the key parameter to decide the property of the thin film. Another one is like among sputtering, this is controlling the gas, and this is like post sputtering. And you could change the material. Different material has different binding energy with oxide. Okay. So these are the knobs, and these are the things that try to manipulate the property of the semiconducting material. This is relatively new. ALD is very famous for semiconductor process. Semiconductor. One more time, this is silicon wafer, atomic layer deposition. It's like chemical vapor deposition, but very controlled. You remove the gas after you have a one layer of the material, one atomic layer. You purge and you oxidize and purge again. So you control layer by layer. So it's high quality. Okay. And they try to do reactant, I don't have time to explain all these things, but reactant selection or layer sequence. This is the way that they control the material. Oh, this one is a little bit old. You know what? People try to use not the vacuum, expensive vacuum system. They try to use solution base. You know, they have acetate and nitrate and all this solution-based material. Okay, you heat it up, boom, weight goes down because the solvent is going, right? And then this range, heat it up, right? So dehydroxylation, dehydroxylation and alloy. This is the part that the material forming, okay? And then if necessary, you can do the crystallization. Okay, this was hot long time, 10 years ago, 15 years ago, and some people even try to come up with a not the toluene or carbon inside the solvent. They try to do the water aqueous. And the very famous group in Northwestern, they're famous for solution combustion synthesis, okay, for oxide semiconductor. Oxide semiconductor, whatever you do, sputtering or solution base, you could start with the metal or you could start with the insulator. Whatever you do, you have to anneal that 300, 400. Then the material becomes semiconducting like this. Okay, this is so people call it activation. Okay. And now this is a recent trend. People try as deposit usually is amorphous, right? But they try to crystallize. But indium, gallium, zinc, they have different crystal structure, different coordination number. So they try to manipulate sometimes, because they have a different crystallization temperature. Okay, so indium, one more time, is difficult to crystallize. I mean, easy to crystallize. And gallium is difficult to crystallize. Okay, and they try to, not only this material, there are other materials they try to manipulate, they try to use. This is one example. This is the recent trend, crystallization of this oxide semiconductor. Oh, this one is still blue ocean. Remember oxide semiconductor, I told you, oxygen vacancy is the keyword. Oxygen vacancy means electron. So it's inherently n-type semiconductor. So people are trying to have the p-type with the oxide semiconductor, but most of them failed. See, like less than 10 number of paper per year. It's very difficult, I think. I've tried skip up now. Cuprous, tin oxide, cuprous oxide, and tin oxide is one of the most represented. But I think many people, the reason is look at this balance band here. This is very localized. It's very difficult. Yeah, I mean, according to Professor Hosono, this is the way that they conducting the the S orbital, the first shell, first subshell uh, through this operable s orbital. But the p has p to p orbital or d orbital. So recently, Chalcogenide material is becoming very hot. Yeah, and we've read some of the, articles and succeeding for P-type, right? So now get back to the application. Yes, first one is display. So in every display, they have a pixel. Every pixel, they have a one transistor. But for LCD, they use amorphous silicon. This is very easy and cheap to make, but there is a limitation of the performance as a transistor. So only for LCD, okay? But nowadays, many people use OLED for mobile and even TV. They use polysilicon. This is much better than amorphous silicon. Like, look at this 200 times higher, faster, the mobility. But still, this oxide semiconductor is amorphous phase, still like 20 times is bigger, higher. Okay. And this is a transfer. This is important actually. Look at this. This is a current voltage. If you put this voltage, boom, transistor on. If you put this one, transistor off. You know the drill. If I put on, the higher the better. If you put off, the lower the better. Which one is good? As far as the law of current is concerned, the green is good, excellent. Green is oxide semi. On current, polysilicon is tops, okay? So for mobile display, yes, people use this oxide semiconductor. Yeah, look at this. Some of you probably do the game with the phone. 120 Hz, very fast. You consume huge battery. But this one, always on. You do nothing. 1 hertz, 120 times per second, you have to give the data. Standards typically 50 or 60. This is very reasonable. MFD. Top view, mobile, high frequency. Still image, bottom, very low frequency. You know why people are trying to do? To save the battery, this is possible because of oxide semiconductors, law of current. Okay. Okay. Yes. You are playing with your phone like this. They are changing the data frequency. So Samsung, they have named adaptive frequency. Since when? 2020. iPhone, they only put this function in Pro model, but recently, last year, they put it in normal model too. But different name. Adaptive frequency from Samsung, Apple, they have Pro motion. So they are changing the frequency. So you know why? Because to save the battery. Yeah, battery is important, right? All right. Oh, this is new. This is really new. Anybody has a S26 Galaxy? No Apple iPhone, only S26. They have a two different pixel. What is this? The person next sitting in the subway, in the bus, the person next to you cannot see your phone screen. The privacy mode. Samsung display have a name Flex Magic Pixel, but anyway, yes, they have like, the OLED lighting is like Lambertian, but you try to limit the viewing angle. So when you need the privacy, you turn off this one. You turn on only this one. So the person next to you cannot see the screen. Right? So I think this one was a big hit. And in the future, even most of the phone, including Apple, they try to do it. But only right now, only Galaxy. Okay. Yes, and this is very recent new trend, high mobility oxide. High mobility. Transistor needs high mobility. Why? Because look at this. This is the transistor size. Yeah, this is smaller. If you have a high mobility, you can make a smaller transistor. Smaller transistor, you can make your phone like this. Which do you like better? I like this better because it's full screen, right? Narrow bezel. Yeah, with high mobility oxide, you could do this, right? So Not commercialized yet, maybe next year. Yeah. All right. So for this is one example, but due to the time, I think I should skip. This is one example. They try to manipulate this crystal oxide semiconductor, and they put the new material to make the high mobility, right? Okay, memory is hot. DRAM, DRAM is hot, right? This is for when you do the control C, right, in your phone or computer. That's the DRAM, right? Volatile memory. Uh, okay, anyway, the cell consists of one transistor and one capacitor. But headache is from both, actually. I mean, silicon, the wafer, the off current is not very good. But this one is even higher headache. Capacitor is very tough nowadays. So the people are using in silicon, but now they're considering this one is not commercialized yet, but people are considering oxide semi for the DRAM. This is the famous AI chip. This is the HBM. Only three companies in the world, Samsung and SK Hynix and Micron, make this HBM. This is the AI chip, like NVIDIA, right? So CPU and GPU in the middle. And if you do the cross section of this HBM, yes, they have many DRAM stack. Okay, so this is HBM, and in the future, one more time, they try to get rid of this capacitor, and even they considering the fully monolithic 3D. So with a wafer conventional crystal silicon, you cannot do it. It's a retention time. You have to keep the minimum retention time. But with this oxide semiconductor, yeah, you can do this 2T0C, 2 transistor 0C. Because this is one application. Yes, this is the by Samsung. This is highly 3D DRAM. And when they make the capacitor, and they need an insulator, but that insulator you need to give a thermal energy. But when you give a thermal energy, become crystalline, boom, this is bad. It's rough, right? Remember VO, oxygen vacancy, as it has bad effect too. It's trapped. So yeah, so you need to control the phase, you know. If you start with amorphous, you have to make sure even if you put the high temperature, that the material stay as amorphous. Or you have to crystallize very early, and then make all the way to the same phase. Okay, so this is another area for oxide semiconductor. Yes, sensor, LiDAR is famous. Already know it's few years ago. And this is by Chinese company. You look at the meter and they tell you your heart rate. How? By skin. I'm not sure. I haven't tested yet. Something like this. And look at this guy. He is holding something. And he can, because of, it's this door open naturally. And you don't need to play with the knobs. Okay, anyway, something like this. This sensor was so photodiode and photoconductor are two terminal device as a vertical and lateral thing, but phototransistor is three terminal device. This is widely used one, some varies, but oxide semiconductor is wide. Comparison silicon is 1.1, right? Most famous semiconductor 1.1. This is why, and material is amorphous. So you cannot play with the visible light. Yeah, no absorption. So you know what people try to do? People try to intentionally create the state. Then it reacts, it sense. Or they put another layer, like, some narrow band material or quantum dots. Quick example is, yeah, subgap engineering is the one that I already mentioned. And this one is the example. This group, I think is in China. Yeah, they put the lithium and look at this. Some amount of lithium, it sends with the light. Okay. And another application, they put the new material. New material, this is by our group. We put the cadmium selenide quantum dot on top of this oxide semiconductor. And because of this, we have absorption. Okay. All right. Last application is a neuromorphic vision computing. Already, automotive, security, and robot vision computing is hot. Okay, so what's the conventional one? What's the conventional? You do have this so many sensors, separate, discrete sensors. You do have a memory and process. What happened? The thing is, you have to still deal with non-essential information. You don't have to process this, but you have to process. So it causes a bottleneck. What about your eye, human eye? They don't do that. They just know what's important. They don't focus on this backdrop. They just focus naturally. That's the human vision system. So people try to mimic human vision. They tried not to touch, not to process unimportant information. That's the neuromorphic vision system. Okay, so look at this, very low contrast, right? Look at this noise. So somebody, your brain, you try to remember something, you cannot do it just once, right? You have to iterate like five times, five times. Yes, this is synaptic. And this oxide semiconductor can do because they do have this persistent photoconductivity. After you do it doesn't go bad. So some people doesn't like this feature, but for neuromorphic, to this, you need this. It's like the human synaptics, vision system, synaptic. Okay. Okay, so yeah, this is also from our lab. We try to put this material sandwiched by oxide semiconductor and show the different wavelengths you can sense. Okay, and you do have this, it's too dark, night vision. You cannot tell. You cannot tell there's somebody. But if you do this, you can distinguish the person. And we check the accuracy and it works. Yeah, this is the one example. All right, I think I almost on time. My last slide is perspective. I just briefly introduced the oxide semiconductor. What's the application display already, but also in the future, new technology. Remember the P-type. This is the completely blue ocean, and the memory is not commercialized, and this is a hot topic too. And sensor, and neuromorphic, I explained. Yes, this P-type one is people have been working on these three materials, but now this chalcogenide material, tellurium, selenide, these are the new emerging materials for promising P-type semiconductor. All right, thank you so much for your attention.
Thank you so much, Professor Kim, for this wonderful lecture.